Perfect.
Yeah, for some reason, my screen, I can't see like everyone clearly. So there's something. Yeah, I don't know. It's maybe just internet speed.
It should adjust, Dikun. It's just because like it's just a tiny webcam, so it's not going to have everybody completely in focus.
Okay, I see. Yeah, now it's better. I think it's just for one moment it's got like pixelized. Okay.
Yeah, it auto adjusts, so you might see it sort of zoom in and out when it loses focus.
Okay. So shall we get started or?
Yeah, sounds good. Do you want to start us off by? I know you've been looking at a whole bunch of things and you've got some specific problems in mind. Yeah, or do you have questions or things that you'd like us to give an overview on first, or?
Okay. So maybe I made a couple of slides. Maybe I can share my screen and so everyone can see some stuff. Where is
So if you mouse over on the left part of the screen, you should see a sidebar pop up.
Screen share?
Yeah.
Okay, I need to find the. Don't see my PowerPoint.
Can you guys hear him over there? We can do it through there. We might. We can try. If you want, we're just going to try. Yeah, no worries. We're just going to try putting you on the HDMI audio. So let us know if it starts echoing like crazy on your end, and I will do that.
Okay.
Let's see. Can you say something? Or, yeah.
Here? Can you see something?
Yes.
Oh, hey, that's much better.
Perfect. And are you hearing yourself echoing, or is that okay?
I think I'm okay.
Oh my God, you sound like God, right? You're just like we're completely consumed by you.
Okay.
We'll do whatever you ask, Dikun, no problem.
I can try.
So it looks like your screen is black right now. Is it black on your end?
So do you hear me better?
Yeah, we can hear you quite well.
Hello?
Yeah, we're here.
So it sounds better or?
Yeah, that sounds good.
Okay, yeah. So can you see my screen now?
It's black right now. Do you mind trying to reshare it or just like close the PowerPoint and open it again?
Okay.
We can see that.
See the cover?
Are you sharing the other screen? Can you move your thing or make a clone of your screen?
No?
That's good.
We see it until you go to presentation mode.
Yeah.
So now the in full screen, right?
That's right.
Yeah, we don't see that. So if you don't mind, could you just show us like in the not in presentation mode? Is that okay?
Oh, okay. Okay, yeah, that's fine.
Yeah.
You can see this, right?
Yeah.
Yeah.
Okay, so yeah, so it's, let me just kill this. You see the stuff? Yeah. Yeah, so basically here I've been trying to do some Marine EM stuff to get some this set inverted, like ideal link 3D. So on the cover here is the picture I took from ESB. And yeah, so here, so ESB is for Empire State Building.
So we're in the same place.
yeah, you're in the same place. Okay, and that's where I got most of the inspiration and ideas. Okay.
You meditate on the ESP, that's great.
Okay, so in terms of solving some Marine CSEM problem, so here's a basic diagram showing the basic ideas. For example, we have ocean bound receivers. So those are the containing electrodes for E field and also sensors on the yellow for the magnetic field. So in particular, for example, if they're doing like a large-scale subduction zone or mid-ocean ridge study, they may want to use a empty source because it can penetrate much deeper. But at the same time, because the empty source can only do like low-frequency stuff for shallow or near seafloor, they have to do a control source EM. That's why they also have the boat towing a transmitter, EM transmitter. And for the hydrocarbon exploration, it's mostly just the CSEM. Yeah, so basically in terms of the demand, you need like CSEM modeling, inversion, and also MT for investigation at different scales.
What's the long baseline navigation? Like, is that a source tool that you have at the surface? Or?
Sorry, which one? The tongue transmitter or receiver?
No, the square that you have beside the long baseline navigation. Is that the source to right at the surface? Yes.
Oh, I think it's
Tracking the transmitter.
yeah, I have no idea. Maybe, yeah, I don't know what it is. I just got this picture from Google.
Yeah, sorry, height.
It could be some navigation system, I don't know.
Okay.
Anyway, so for this kind of problem, so basically we can talk about three difficulty or challenges. First of all, it's a towed system. So usually it covers like hundreds of kilometers, like that kind of scale. So it's really large, so it's a large scale survey. And also we need a journey version. Because for shallow part, we can only use CSEM, but for deep part, also need to include MT information. So ideally, you should be able to do MT and CSEM journey version. And for CSEM part, there can be frequency domain or time domain. Yeah, so in reality, people have collected both frequency domain and time domain CSEM data in Marine.
So Dikun,
yeah,
like it's usually frequency domain, right? Their system. Do they have?
Okay, so 95% frequency domain CSEM,
right?
And maybe I don't know 5%. So they're experimenting some time domain system. So carries down some tests. So they were able to see the time domain system is better can have better signal-noise ratio, or because for some reason frequency domain system may lose phase information for high frequency or short offset. So the phase information is basically missed. So they have to do some time domain system. So anyways, so in the future it could be time domain system. And also for Marine environment, it's highly stratified. So of course, anisotropy is a big problem. Need to think about. Yeah, so this is especially true if we're doing the global and local mesh decoupling. For the modeling mesh, the global mesh, we're going to have a large cells to represent a small cells in the inversion mesh. So in that way, if the layer, the seafloor is highly stratified, so the upscaled conductivity certainly has some anisotropy. So next is some framework I've been thinking about. I call it the D-cubed approach, because that means decoupled, distributed, and desynchronized. So here's the diagram I borrowed from the SimPEG framework. So I'm sure most of the stuff on this slide has been thought about or even implemented within the SimPEG framework. So I'm just repeating maybe some existing things and just saying something I've been thinking. And if you guys have any idea, for example, if I've done this or is going to do this, maybe just feel free to interrupt me. Yeah, first of all, we're going to have a decoupled for the modeling version. This has already been done in the SimPEG framework, we have 4 simulation and inverse elements. So this part is perfect. And so what's important here is have a universal and a cross-platform interface. So I think SimPEG has done a pretty good job in making the interface very universal. You can change different for the modelers but just plug it in and use the same inversion engine. So that's good. Another thought in my mind is maybe we have to think about like cross-platform interface. So you have, for example, your inversion engine in Python. Maybe one day you want to use for the modeling code written in different languages. This is especially true here because most of Keras code, finite element code, 2D or 3D, are in Fortran. So changing everything from Fortran to Python is not going to happen in a short time.
Yeah, and so, since I'm just going to jump in here. So since the forward simulation actually is fairly well decoupled from the inversion, and Python is a very good glue language, meaning that it interfaces nicely to other software. So it, like that step would require a light wrapper to interface to Fortran codes.
Okay.
So there's some stuff we need to do under the hood to clean that that gluing up, but yeah, that's totally possible.
Okay, good here. Yeah, it's good. And yeah, so just ideally, I wanted this framework to be able to communicate with all basically existing for modeling code as long as they obey the same interface or same designing or like API or whatever. So you can talk using the same language. So so I think that's good. And next
jump in again. Do Keras codes, they all have sensitivities? Or we would need to do...
So for the 2D code, yes, I think they do have everything. They have all the necessary ingredients.
Cool.
Yeah. But the thing is, the things are kind of native in Fortran, and the things are kind of like only connected internally. So there's no external API to be called. So that's something you need to work on.
Okay.
Yeah. And the next thing is, what if we have some exotic modelers? For example, if we have a meshless for modeling, we don't necessarily have a mesh. Or yeah, just for example, recently I've been looking at using machine learning to do the for the modeling. So in that case, where I was not actually solving the PDE, so it's basically just train the network, and eventually the network can take any input model and spit out the response. So there's no PDE solving. So all kind of like exotic modelers, maybe just make a uniform interface so they can be called.
Yeah, so I would say that we're close to that. We're not exactly there. There's an issue, I don't know if you saw that one, the problem with problem. I can send you the link. And that, once that's implemented, the forward simulation really will be a lot more walled off in that sense. So as long as whatever you give us for a modeler, as long as we can get predicted data and sensitivities and an adjoint out of it, it doesn't matter what's going on under the hood.
Okay, that sounds good. So the next item is atomic decomposition. This is something I've done in my thesis. As I consider this is the most important finding in my thesis is if we want the best efficiency, we have to break apart the whole problem as fine as possible, as fine-grained as possible, which means we model transmitter receiver pair at only one frequency or at only one time channel for each sub-problem for best efficiency. So this might not be difficult to implement. Maybe it's just, yeah, I think for the modeler, you just only model one frequency or one time. That's probably simple. The next thing is called fully non-conformal global local transform. So this kind of become necessary because if you think about like airborne EM problem, so the transmitter receiver same location, So when making a local mesh, it's relatively straightforward, but for like for Marine EM or CSEM, the transmit receiver is sometimes can be like 4 kilometers apart. So when making the mesh, we need like a locally refined thing, or yeah. So the global local transformer can sometimes it's not straightforward, and also if we take into account anisotropy, so that I believe there must be some sort of work need to down in order to do this, because the existing thing formula for me is to do the volume-based averaging. So volume-based averaging doesn't take into account the geometry of the fine cells or fine structures. So for the marine CSEM, it's horizontally layered, so there's anisotropy we need to do if we're going from global to local.
Yes, so that step hasn't been implemented, but we might jump in a bit and talk a little bit about, we have the volume averaging that you're doing. So we do have the volume averaged global local setup. It's not in the core SimPEG yet, but that's sort of been thought through. And so extending that to the case where you actually want to upscale into an anisotropic model, we can sort of show you where that contribution would fit in.
Okay.
Yeah.
Yeah, that sounds good.
And then anisotropic modeling is hooked up. So as long as you know, like as long as we create the steps to build your anisotropic conductivity model, the forward simulations can handle it.
Okay, that sounds good. And another thing is by saying non-conformal, which means the global local can be in different coordinate system. There might be some rotation. Yeah, especially if we think, for example, this picture, the transmitter up here, receivers here, with an offset both horizontally and vertically. So depending on what kind of a mesh you're going to use, for example, if you use an octave or like an unstructured mesh, probably you don't have to rotate anything. But if you use a tensor mesh or a structured mesh, probably have to do the rotation to minimize the number of cells in the local mesh. And another point here is to invert out data without modeling of them. Yeah, so the idea is simple. So you just, the early iteration, you only invert maybe model 10% of data. Later on, you're doing the fine scale structure. You gradually add more modeling to the inversion. So basically, it's kind of like a multi-level or multi-resolution thing. So, but I think if we have done the decoupling here, so we have a full control over which data we want to model.
And Dikun, so there's a lot of things here. What are your priorities?
So this is only the small part of the thing. So I'm just laying out everything I've thought about. Yeah. And then I'll do the priority later. Yeah. So what I'm saying here, just ideally, I want a code like this. But to make it happen is another story. So I'm just doing my imagination here.
Yeah, well, what I think is really exciting about this, Dikun, is that although I mean most of this hasn't necessarily been implemented in SimPEG, there's places for all of this, and they're modular pieces, so it's not like you have to implement everything from like start to finish. Okay, good. Yeah, I figure for most of the stuff, people have been thought about it. So it's basically just working on existing thing, or maybe just make some corrections or make some changes to make it happen. So that won't be too hard. So the next one is, I think, is more. So it's kind of a relatively big deal. So, so now on the right, I'm comparing two different paradigms here. So one is a server-based, another is P2B network. So the current framework of parallel computing is, at least for EM inversion, large scale EM inversion, is for this kind of server-based thing. So I have a master thread dispatching jobs to different agent workers, and once the worker done the local mesh or local problem, just send back the result to the master, and the master is gonna do the model update and send the updated model back to them, and they work on it, just iterate. So there are lots of overhead in the computing. So lots of issues in the load balancing.
For example, you want to do the dynamic scheduling or static scheduling, the response counts, all those configuration. So another thing I've been trying to do is do like a P2P based inversion. So all the P2P agents are equal. There's no master. So the job is done collectively over the entire network. So the biggest motivation for doing this is because the synchronization is the bottleneck of scalability in 3D large scale inversion. Just because the master need to send out the information to the workers, and once the information sent out, the master just wait there, just waiting for everyone to return result. If for some reason a couple of the workers is slow, it just slows down everything. And just because everything needs to be perfectly synchronized, and so I have to do this sequentially. So if we move everything to a P2P based network, so every agent, P2P agent are disposable and replaceable. So there may be some duplications here. So this one maybe are pretty much doing the same thing, and they are just updating the model or updating the inversion without any gap. So once this one is done the job, it can start working on the next thing. And so the nice thing is about this network is it can be highly redundant and resilient. So if for some reason a couple of nodes got crashed, so inversion is still running. And if later on I got additional 500 nodes from Amazon, I can use them as an additional resource to speed up my work. And if later on I have a tight budget, so I don't have those anymore, I can take them off. The inversion is still running somewhere else. So it's basically just making inversion, especially this is geared towards mostly for large scale inversion for a really large problem. So in the next slide, I'm gonna just show you an example. Just for example, if I want to invert the data of entire Canada, so what's gonna happen? So I'm showing here is a map of West Canada. Supposed to have I don't know, airborne EM data across the entire Canada. So those agents are only gonna do a regional inversion. For example, I'm now picking an area around Kamloops. I want to do the inversion around Kamloops. So this agent is gonna look around because the Kamloops need the information for the starting model, so the current model. So it's just find out, oh, there's an agent working on Prince George, agent working on Vancouver, agent working on Calgary. So the Kamloops just communicate with those three cities and get information in this region. Then the Kamloops can start working on updating the model around Kamloops. So once the Kamloops model is updated, and so the agent that was working on Calgary is already done the Calgary. So maybe this agent now moved to Edmonton. So so in order to get Edmonton inverted, so you need to look around for, okay, I need the information from Fort McMurray, need the information from Kamloops. Oh, that guy just done calculation on Kamloops. I can just directly talk to the Kamloops and get the updated model, and the Edmonton can continue working. So you can see this one can happen across the entire network. So while those agents are working on the West Canada, there are a bunch of other agents working on Toronto, Winnipeg, or St. John's. So in this way, so the network basically collectively working on inverting the entire Canada. And there's no waste time in waiting. So the loads are automatically balanced. So all the activity can be logged like in the matter very similar to blockchain. So everything can be retrieved. So this is just a very brief description of what can happen in this kind of framework. So that's about it. Maybe just move forward.
So, Dikun,
hi.
Do you have an example where a P2P network problem has actually been solved?
P2P is a decades-old technology in like computer network, but I don't know any application in geophysical inversion. But there's tons of application in just transferring files across network. So this is
do you have like a machine learning example or like something where a serious computation's been run in that sense?
Sorry, can you try it again? Hi, Lindsay.
Yeah, do you have an example, like even from the machine learning world or something where like a serious computation has been solved in this sense, not necessarily just a file sharing or like a query?
No, I don't have it now. But I know the technology has been existing for a really long time. And maybe there's something we can just borrow from them.
But so if I think that as just asynchronized problem, is that basically same? Because like you can think about the server base also synchronized or asynchronized. Because like if there's one worker is not working, we can force them to work, right? So if there's an option, you can make it synchronized or asynchronized. So is that still server based or that's the P2P?
Yeah. So can you repeat your question again? Can you speak slowly because I'm hearing a lot of the echo here.
There's kind of two options, like a synchronized or asynchronized. So like if you run some sort of parallel algorithm, there's an option, right? Synchronized means like you kind of ask one worker or multiple workers, you need to wait until all the workers done the job, right?
Okay.
But the other option, asynchronous, like you can just say workers, just do whatever you want, and then don't stop, just work, right? Like is that the same as P2P?
So the most important thing in P2P is there's no master. So everyone contribute to the network, and the whole model existing only on the network. So any single agent here doesn't have the entire picture. It only has the part of the picture. But if you consider them all together, they have the whole picture. I think this is the most important part for P2P. So this allows them to communicate like from A to B or to C. They don't have to all talk to the central master.
I guess the big question, Dikun, is how you handle because you need somehow to store the final answer, right? Like it's blockchain, you only need to solve like to send like.
Yeah, I think for the blockchain is the way to record who does what or who did what, and the actual model are actually distributed across the network. So none of the agent here has an entire model, just because the model is large. I'm just talking about a really large inversion. And then none of the agent here has the entire data set.
Yeah.
Okay, but what happened if you start with 100 workers, you ramp it up to 1,000 workers, and eventually you end up with 2 workers. Now everything is living on 2 workers. Like, how do you handle memory? I'm curious if you ever thought it through. Or...
Yeah, so it's a very likely issue. So there are lots of duplications. For example, so can loops, it could be like 5 workers working in their area closed can loops. They're gonna do their own model update. So one way you can do this to use a timestamp to make the priority, or like maybe just in simplest case, just average them. So there are lots of detail need to be figured out.
Yeah, that's exciting for sure.
Yeah.
Being pulled off, that's good.
Do you have a motivating, a specific motivating example that would have cropped up, at Woods Hole, or something that kind of anchor ourselves as to what we'd like to do and how to proceed?
I think the best example may be some large airborne EM dataset. For example, the one at the Pebble. That one is really large. That could be example. And also I have to know there are some like SkyTime data from Denmark that basically cover like half of the country or something like that. that could be a good example. Here, I'm just making a very extreme example showing like entire Canada or West Canada, but this is a just a scale, different scale. So yeah.
Fair enough.
Yeah.
So here some questions. So if we want to move forward, my first question is, what's the current status of MT or CSEM for the simulation? Like something in this box. Because
we have the MT code. Sorry, I'm just going to turn the mic. We have MT, and we have the ability to simulate CSEM hooked up. There's a bit of cleanup that needs to go on in the MT code. It has a bit of a different feel right now than the frequency domain EM code. Not too much, but there's a few things that need to be cleaned up there. These are hooked up on tensor meshes, off-tree meshes, like any mesh that's in discretize at the moment. Right now, we wouldn't necessarily, like, we're working on getting to larger scale. The code is not currently parallelized, so that really does limit the scale of what you can do with it right now. But I'm sure you saw last week's meeting that we're now sort of in a place where we can start to think about parallelizing and how do we go forward with that. We have infrastructure in place to do joint inversions. That's not something that's been hit on too hard, but the infrastructure's there. Do you have any other questions on?
Yeah, because I've seen some the documentation webpage. I've seen lots of 1D things, but I don't see a 3D example or like the stuff. So is there 3D example? Because I know Thibault sent me something he did for the time domain EM. Is that just Thibault's his own work, or like is it gonna be merged one day, or people are actually on the development branch, or is just something has to be done?
So what I sent you was just because you asked just for the operator and if we can use the operator separately. So I sent you that project that I did, and that was only using the operator from discretize, but time domain EM is in SimPEG, so like don't use my own little project.
Okay, I see. So for myself, in terms of getting started, I basically just need just assume this has been done, MT or CSEM for our sensitivity calculator.
So, Dikun, I think probably the good place to start, because you have some problem specific. I think SimPEG was kind of developed for airborne in the beginning. So we got most of the stuff for airborne, and then maybe build a bit of grounded source, but not quite for marine, because there are some specific things, right? You compute like the kind of primary field. I think it's probably a two-layered Earth, right? You've got air and the sea. Maybe sea sediment as well as a primary field. I'm not 100% sure how that's been done. So there are quite a bit of details of how marine CSEM works in the for simulation sense. So I think that details may not be in the current SimPEG. So I think you probably need to map out how that really works. And then I think kind of making that core simulation for marine CSEM really works in SimPEG might be a good starting point.
Okay, yeah, probably because I'm new to SimPEG, so this can be different. So I have been using the Julia package, to solve some like the airborne and the marine CSEM problem. So under the framework of Julia code, they are very similar. So you just implement a different source. Yeah, either just a finite line source or just a loop source. So loop source means you just square, like four-sided a loop instead of just one segment, have 4 segments to make a loop. So in the Julia package, it's just that kind of difference.
Dikun, do you use a primary secondary approach, or do you just forward simulate with a finite line source in whatever space you're in?
You mean the Julia or?
In general, or in Carey's codes?
I believe it's total field.
Okay.
Oh, Carey's
So
code?
that's set up.
Well,
Yeah, I don't think Carey's code is total field. I think it's they are using
Primary secondary?
primary secondary. I think that's usual for Marine EM, as far as I know.
Oh.
So you probably need to kind of check, because you need to choose the right way, and I'm not quite sure what's the best way. So you probably need to choose that part, and then that might kind of direct a little bit differently.
Okay, so I'm wondering if there's an existing thing in the current code base already implemented, like CSEM can be either airborne or whatever. So something I can take a look, maybe just change something so it works for Marine CSEM. Maybe that's the fastest way to get things done, or?
Yeah, that's true. And then there is a code, as you would remember the line current stuff. It's in SimPEG. There is a code that you can use it. It's only working for tensor mesh, but there is, so you can kind of use that for Marine EM.
Sorry, so okay, you have to repeat. Your voice will cut off.
There's a line.
Move mic right up to you. So.
Can you try say it again?
Yeah, there's a line current source. So basically, you can do the same thing that you do in Julia in SimPEG. So you don't really need to redevelop that. I think that was one.
Okay. Yeah, so there's already some 3D codes, control source EM code, not necessarily for Marine, but just the generic.
Yeah.
Okay.
Well, so supposed to work for Marine EM, I think, but we haven't quite tested that. That was my point. You really need to test it.
So do you have, sorry, I'm really loud, so it's my there. Do you have an example that you could send to Dikun, like the grounded source one? I'm thinking the one from the disk is the grounded source with the block, because that was a full 3D problem.
Yeah, yes. I do have an example. I think for both frequency and time. Yeah, I think so. Dikun, I can send you an example.
Okay, sounds good. Yeah, so that'll be really helpful if you have examples, maybe templates, or like even just manual or something I can just follow. So so make sure I understand if I do this type of coding, it's kind of like in the SimPEG fashion, or like it's not violating any assumptions, or like not violating the style.
I'll send you, there's another example we have that uses the cylindrical mesh, but you could swap it out for a 3D mesh.
Okay.
That really explains step by step what's going on. So that'll give you a feel for the terminology and like how we set up a simulation and an inversion. And then that coupled with the example that Soggy sends you will hopefully get you pointed into how to set up a 3D example.
Oh, that sounds good. Yeah, that's probably exactly what I wanted.
And you've seen the SimPEG examples, right? I know there's not tons of them there, but there are a few.
Yeah, I think DC.
Yeah, I've seen them. Yes.
DC has quite a bit of 3D. I think Thibault made a bit of 3D example. So the field is pretty similar. Like the problem will be changing, but how the mesh is set up, how the survey is set up, problem set up, it's quite similar.
Good. Yeah. So maybe send me the template or examples. So another thing I need to do is to get used to the terminology here, like because I realized there's some, yeah. So like inner product thing.
That's a nice matrix.
It's then I wasn't sure what it means by inner product at the beginning, and then I realized it's basically something I've seen before. It's basically just integration of
yes.
to do the basically averaging matrix. Is that right?
Yes, that's true.
Yeah, it's your physical property matrix.
Okay.
The inner product terminology comes from the weak formulation.
Okay, that's fine. Yeah, that's okay. As long as I know what it is, that's okay.
Yeah.
Good. And then maybe the.
Do you have both the EM paper and the first SimPEG paper? I think I sent them to you.
Yeah, I read them. Yeah.
Cool. Because that actually outlines some of the terminology as well.
Yeah, that's how I figure it out.
Your leading edge paper.
Or leading edge paper.
No, there's the first one, right? The
the
pixels, and I think that's where there's in product technology.
Yeah.
Maybe the last question is like the highlight here. So if I develop something, how do we determine it's part of the SimPEG code base, or maybe it's just like a new standalone package with a label like SimPEG certified or SimPEG like a based package?
So that really depends on the scope of what you're doing, Dikun. So if there's something like developing a new source, like if you want to do a primary, secondary approach for Marine CSEM, that would be developing a new source, and that fits right into SimPEG. Mm-hmm. If you want to try and build a P2P distributed parallel solver, that's probably like on top of SimPEG.
Okay.
And so these, I think, are just like as things come up, we'll chat about it and we'll find the right home for it.
Okay, I think that sounds good. Yeah, my general thought is if a procedure or new code is very generic, or maybe likely to be recycled, reused by lots of other people, maybe it's good to be part of a SimPEG code base.
Yeah.
If it's very specific, for example, only solve a very particular problem, it's better to be a standalone package.
So I guess like and I think this is what you're saying, but it's basically like if it's a reusable piece, then it can go in SimPEG. If it's like you're writing a script to actually solve a specific style of inversion, then that probably sits outside.
Okay.
But we can figure that out as we go. Are you on the SimPEG organization on GitHub? If not, I will add you.
Yeah, let's double check. I'm not quite sure.
Okay, so if you just send me your GitHub handle, I'll add you so that you have push access to SimPEG. So we don't let anybody push directly to master. You'll have to just branch off and build from there. And then, because we do, like anytime that there's new code coming in, we'll peer review it and make sure it hits sort of testing standards, style standards, all of that. And then before it comes in. So that's a bit of the workflow there. There's a write-up in the docs about that a bit too that I can.
Okay, sounds good.
Yeah. Okay.
Yeah, all right. That's probably, that's it. Yeah.
Cool. That's exciting.
Good.
Do you have any other questions, Dikun?
Not really. Are you guys still gonna continue the meeting or?
Yeah, every Tuesday.
Oh, I mean today. I mean, are you gonna wrap up today or?
Oh, I guess are there other things?
Probably should.
Yeah, fair enough. Is there, before we end, is there anything else people wanted to go over before we finish?
Can we just sort of summarize on like what the simplest problem at this point is that Dikun would like to do? I mean, is it basically a grounded source in water?
Yeah.
Relate the fields from that? And is that it?
Yeah, I think that's what I'm looking at now.
Dikun, do you have like a simple sketch of maybe a 3D problem that we could help you set up?
You mean the survey or?
Yeah, and a model. Just like, you know, there's maybe the canonical sort of Marine CSEM problem, but then make it 3D. Do you have an example of like the right scales and a simple survey, like a line of data?
Okay, I'll have to look. Yeah, maybe if I send you something, maybe tomorrow when I get into office.
That'd be great, especially actually if there's something that Carrie has used to benchmark his codes, and then we could make sure that we're all on the same page and getting what you expect to see.
Okay, even just some sketch diagram is okay, right?
Yeah, absolutely.
Okay, all right. Yeah, I'll figure it out.
Okay.
Good.
Because it's actually, I mean, if we talk about the 1D case, then there's actually quite a few benchmarks that could be performed on that.
Yeah.
Even bigger scope, right?
Yeah, absolutely.
And yeah, to then put a block or something else in there.
Yeah.
So I'm closing my sharing, or okay?
Sure.
All right.
Okay.
All right. Thank you, guys. Bye.
Any fun? Say
Good luck,
hi to
Sogi.
Matt.
Thank you. Goodbye, Sogi. Send me the link.
Well, yeah,
Good.